Hello and welcome to this JuliaCon talk on UnitJuMP, a new package for automatic unit handling in JuMP models. My name is Truls Flatberg and I'm a senior research scientist at SINTEF, one of Europe's largest independent research organizations. As part of our work, we develop optimization models both for industrial use and research projects. Traditionally, these models have been developed using commercial modeling languages, but we are now moving towards open source alternatives, including JuMP and Julia. Real-world optimization problems involve physical quantities with units, both for the parameters and the variables, and this can cause problems along several dimensions. Correctness: the constraints have to be dimensionally correct. Consistency: for example, input data can be provided in different units. And scaling, where generic models with fixed units can have scaling issues if we change the application area for the model. While commercial modeling languages have little or no support for modeling of physical units, Julia has excellent support through the Unitful package, and the ambition of this package is to support this in JuMP models. So, what functionality does UnitJuMP bring to the table? It provides support for defining variables and constraints with units using the normal JuMP macros for defining variables and constraints. If a constraint involves parameters or variables with units, the package will ensure a consistent scaling of the constraint. Units for the objective function cannot be given directly, but there exist workarounds. And the package is currently limited to linear constraints. The following shows a very simple example on how to set up an optimization model with units. We have two variables, x and y, with different speed units. The unit for x is meter per second, while the y variable is given in feet per second. In addition, we have an input parameter, max speed, that has the unit kilometer per hour. These can then be combined in constraints in a consistent manner. In the first constraint, we explicitly set the unit used to be kilometers per hour, while in the second constraint, no unit is provided, and then the package will use the unit of the first variable occurring in the expression as the unit defining the constraint. In this case, the constraint will be defined and scaled according to the unit of x, which is meter per second. Similarly, the objective will use the unit of the first variable involved. In this case, it will be defined by the x, and it will also be using the unit meter per second. So, running this example, optimizing this model, we see that we get optimal values for the variables in the correct units. In this case, the x variable gets a value in meter per second, while the y variable gets an optimal value in feet per second. Similarly, the objective value is provided in meters per second. So, how is this package implemented? Well, under the hood, the package wraps the JuMP variables and constraints with the corresponding unit. The use of these types are then supported by the mutable arithmetics interface, and they can also be used for basic arithmetics. This allows us to use the JuMP macros also for the new types, as well as forming expressions from the variables. The following little example shows a model with two variables, v and w, the first provided in meters and the second in feet. The type of a single variable will then be a unit variable ref. While if we add two variables into a single expression, the type will be of the unit expression type. The following shows a bit a more realistic example of using UnitJuMP in an optimization model. In this case, based on an energy modeling example. In this example, we have 3 time periods where the duration of each time period is given in different time units. The 2 first time periods are given in seconds, while the third one is given in minutes. These parameters can be used in the model without thinking or consideration about the units, as this will be handled automatically by the package. In this case, the duration input parameter is used to update the state, in this case of a battery, depending on the charge rate or discharge rate over the duration of the period. In this way, complex models can be checked both for correctness and consistent use of units. So try out the package yourself, give it a test ride. All feedback and PRs are highly appreciated, and with some positive feedback, hopefully we can find the time to extend support also for quadratic expressions. Thank you.